Hi everyone. Today I will present the topic about representation learning for reinforcement learning. So first, I will want to talk about the general framework in the reinforcement learning. In reinforcement learning, we usually formulate the process of the data and the agent interacting, like the Markov decision process, and this process includes four main components. First is S is state space, A is the action space, and P is the transition probability, and R is the reward. Usually in the reinforcement learning, we assume that the transition probability P which is unknown, and an extension of the Markov decision process is the partially observable MDP or the PAMDP. And in this process, it also includes four main components. But one difference is we don't know the exact state, and we only observe the partial of the state, and we call that O, which is observation space. And the final goal of both framework is we try to find the policy that maximize the expected return, which is defined like this. And the gamma with the gamma discounted factor for the k of the infinity horizon. And to evaluate the performance, we usually consider two score or the two quantities. First is the score, which is the total reward in an episode or the return. And the second one is the sample efficiency, means how many samples we need to reach the certain performance. And the solution for these two problems can be model-free or model-based method. And in the model-free, we don't know about the true transition probability. Actually, we don't use that. We only use the sample from state, the action, and the reward to learn the optimal policy. And in the model-based method, we try to learn the transition probability, then use that transition probability to planning. Okay, so this is general framework. So one case study of the past PAMDP is the vision-based reinforcement learning. So in the vision-based reinforcement learning, we assume that we only access to the observation, and we cannot access the true state, the underlying state. Bottom left finger here is the general framework or general diagram when you solve the reinforcement learning. And the state here is some vector, and it go to some reinforcement learning algorithm to find the optimal policy. But when you solve the vision-based IL, first we usually put the observation into the encoder, and from the encoder it will output some feature. From that feature it will plug into the reinforcement learning algorithm block. So to solve the control that directly from the visual observation, we usually need to find the good representation or the feature that reflect the true underlying state here. So this is one requirement. The second one is we want to require less number of sample. It means that the AI algorithm should be efficient, so it can reduce the sample complexity. And one more is we want to find the robust representation such that it can robust again to the distractor. So there are three main approaches for address this problem for vision-based IL. To learn the good representation, we can learn the feature extractor by using some auxiliary tasks. And the second one is we use the augmentation for IL. And the third one is the unsupervised IL. First, like the popular auxiliary task for this problem is using reconstruction loss. And the example of reconstruction loss can be the variational autoencoder or the simple autoencoder. For the variational encoder, many previous talk try to use that, and they said that the variational autoencoder is unstable. And recently, there one paper named the soft actor critic autoencoder SAC AE here. It introduced another loss function for the auxiliary task, and they figure out that the variational term in the objective of the VAE really caused the unstable during training, and they propose to using some regularized autoencoder, then it can achieve more stable training. And here is a proposed objective function for learn the auxiliary task. The next paper is STDIM. It is a spatial temporal deep informatics. The deep informatics is the one paper in the computer vision. They also propose one self-supervised learning algorithm that try to learn better representation. So the question here also, what is the best auxiliary task? And this one propose one way. Basically, they propose to use the global local objective and the local objective that is try to maximize the mutual information in the local and in the global. So basically, first, to measure the mutual information, recently we have the very famous tool is the NCE, non-constructive estimation. So you guys know about that, right? In the global local objectives, we want to maximize the mutual information between the global feature with the local feature. So local feature, it means that they divide the feature at some hidden layer, such that it has multiple patches, and they maximize the global feature here with the each patch in the feature map. And they're also using the NCE to the non-constructive estimation to maximize the mutual information. And for the local objectives, they already maximize the equivalent feature. So the next paper here, is also using the constructive loss to learn learn the feature at the auxiliary task. And this paper is quite similar with the SimClear paper and MoCo paper. In this paper, they try to apply the constructive learning to learn the better representation here. So they learn better representation here by contrast between the by contrast between the different view of the same image. So start from the observation, it will generate different augmentation version, and then they encode by different encoder, similar with the MoCo, the encoder, the normal encoder, and the momentum encoder. And then we obtain two query and key, and then they contrast us. Yeah. And using this one also for reinforcement learning to learn. So similar with the SAC AE autoencoder, the constructive loss and the reinforcement learning loss backpropagate to the encoder concurrently. And this is a result of this paper. You can see in the right finger here is the learning curve of them. They compare between the learning from state and learning from the image. So two of them lie close together. So it means that when we learn from the image, we also can reach the performance similar with the handcrafted state. Yeah. Okay, so the another paper. The main idea of this paper, they want to learn the feature such that it can reflect the predictive information. So what's the predictive information? The predictive information is the mutual information between past and the future. And in the context of reinforcement learning, you can understand past and future is the current state and next state, like the two images. We want that two images in the feature space, it should be predictive. It means that from current state, we can predict the next step. Yeah. So and one another thing is they want to learn the compressed representation of H. So it means that they only the representation of H encode only relevant feature to predict the variable y. The two motivation of this paper, and to do that they use the conditional entropy bottleneck. It is basically this equation. So H and Y here, you can easily understand is the current and next state, and Z here is the representation. So to satisfy the predictive information, we minimize this term. It means that we maximize the mutual information between Y and Z here. It means that we learn the representation Z of Y such that it is used as useful as possible to predict Y. And in this term, we want to compressing away any information from X. It means the given Y, the mutual information between X and Z should be small. So this will be the auxiliary task in this paper. They propose this one. The auxiliary task it performs this one. So we can satisfy two property: predictive information and compressed feature. So how to optimize this? They approximate this one by this formulation. It's just from some paper. They prove that. Yes, and actually the author of this paper also the second author of this paper, and yeah. So the main idea is like this. And to optimize this one, they also use the non-constructive estimation (NCE). And here is the result of this paper. Okay, so the next paper also propose another way for the auxiliary task, but this one in the different way. Yeah, previous work, all the previous paper I presented, it learn the representation that perform a task, right? Perform a auxiliary task. It means that the feature here should be used to minimize some task loss here. But this one, besides that, they embed a metric to learn the feature better. The B simulation is a metric measured by this one, by this term. And another auxiliary loss is they want to, in the latent space, they want to L1 between two arbitrary feature should be follow this metric. So what is the B simulation? I can say a bit about this one. In the B simulation, we need metric to measure the two states that have the similar behavior. So what is the similar behavior? You can see here is the visualization of the latent space after learned by this metric. You can see in this two states, it has a similar pose, right? This robot and this here is different observation, and it has similar pose, but a different background. But this one can learn that close in the latent space. Yeah. And this paper is also the oral spotlight paper in the ICOR 2020. 21, I remember. It's just last year. Yeah. So one thing is what's the benefit of this loss function? This one can learn more robust representation. It means that it can learn to ignore the distractor, different background but the same robot. It also can learn. So this is quite this is like the state of the art of this. Yeah. And here is the result. The next paper is a different approach. Previously, I mentioned about all of the previous paper is for the auxiliary task, and this one is just apply augmentation. So, yeah, in my opinion, this is quite simple paper, and it also can be published in Knowledge to this paper, published in Knowledge. I think I don't need to explain anything about this paper because it's quite straightforward. And only one thing about news. Both of them is published in Knowledge. But why this one? But it's not really identical. It also is augmentation, but this one has some new thing. Is they apply some regularization, and the philosophy of this, the principle of this regularization is they want to output of Q value should be invariant to the transformation. So it means that the output of Q value it should be remain without regardless the transformation. Okay, so the final approach is unsupervised IL. So you guys usually heard about the unsupervised learning, right? Self-supervised, unsupervised learning and supervised learning. So what is the unsupervised IL? So actually, you can think the reinforcement learning like the supervised learning with what the supervision signal is the reward. In the supervised learning, the supervision is the expert label, right? Expert annotation, like the label, what is the which class, cat, dog, and everything. But in in reinforcement learning, what's the label? Label is the reward. Yeah, and unsupervised learning, unsupervised reinforcement learning, it means that no reward. Yeah, so without reward, how can we learn? So this is one like the comparison. The feedback here, it means that the label. So we learn with the feedback and we active learning, it means the reinforcement learning. But we learn with the feedback with the passive. It means that like the immediate classification, this is supervised learning. And without feedback, passive, this is unsupervised learning. And the final thing is without feedback but active, it is intrinsic motivation. But yeah. So what's the intrinsic motivation? You can understand like the baby when it's just born, you don't know anything. So how it interacts with the environment, just try everything new. But if don't know any like the reward, right? Just play, self-play. Yeah, and it so what the encourage they do that the try. What encourage they do that is the new thing. New with what? New with baby itself. Yeah. So in the unsupervised learning, they use intrinsic reward. This one kind of reward that is opposite with the external reward. The extrinsic reward. The extrinsic reward is the reward from the environment. and the intrinsic reward is the reward from the agent itself. And how we use that? We can interact with the environment, freely interact with the environment to explore the new from the environment. And we want use that kind of reward to learn the general thing about the environment. Yeah, and one example is like this. So without the intrinsic reward, we explore only the reason, the small reason. But with the intrinsic reward, we scatter. And yeah, intrinsic reward, maybe you guys don't familiar with this one. So it may be like the strength term. Don't know what is this. So can you feel about that? Like briefly understand what is the intrinsic and why we need that and why we have that. Actually, this one is not new. It is really old problem. But recently, many people use us. So, is there any question about intrinsic reward? Usually in IL, when we interact with the environment, we get the reward, right? The reward from the environment. So we use that reward to learn. But without reward from the environment. So how we learn? Is the purpose of the intrinsic reward. Like learn general thing. Not interact, freely interact without role, without purpose. Yeah. So to create that kind of intrinsic reward, we can one example we encourage the agent visit diverse observation via the pseudo reward, and the pseudo reward can be the inverse of the density of the observation or using the entropy of the observation. So we can use the entropy to like the pseudo reward. One problem of this one is when we use the entropy with the high dimension state, it means that the image it is intractable to compute the density. So one way we can use the alternative is the nearest neighbor based entropy estimator. So this one definition like this. These are another way to estimate the entropy. And basically this one, it is proportional with this one. So this kind of reward can be quite easy to learn in the high dimension state. So this is one paper, recent paper in ICML 2021. Proto, they propose one way to learn the representation without reward. Swap is one kind of constructive learning, but learn in the clustering base rather than using the noise constructive estimation NCE. In this term, it looks complicated, but almost it is constant. Only this one, the R here, it is variable, and the other term is a constant. So basically, we use this one to estimate the entropy. We can just use this term. So two purposes here: learn the policy and learn the representation. But learn the policy here not for any specific task. It learns for no task, for the pseudo reward here. And here is the result of this paper. Half the time it is for pre-training, and the rest of the time it is learn for the specific task.